Okay, let's go over what are the various combinations of a 6-carbon monosaccharide with 4 chiral centers, and if there is an easy way to extrapolate all of them without wasting too much time with either trial and error or with memorization. So I've asked this question of myself, and I feel like I've come up with a reasonably easy answer. So when we're dealing with monosaccharides, first question is, well, what are 6-carbon monosaccharides with 4 chiral centers? Really, we're talking about things like glucose. And there's a diagram here already to help you imagine it. But all these diagrams have one thing in common. They are Fisher projections. I believe that's written like so. Fisher projections. And they're, in my belief, they're one of the easiest ways to draw what you really need to without wasting too much time with pen and paper. So let's look at a generic Fisher projection, right? There's a aldehyde group. So we know the aldehyde group generally looks like there's an R, right? And that's attached to a carbon which has a double bond to an oxygen and then a hydrogen, right? That's an aldehyde group. Another way to draw an aldehyde group is actually to put 2 hydrogens. That's also an aldehyde group, but this is just one type of aldehyde and that's it, you're done. Whereas this one can give you n numbers of aldehyde because the carbon chain can be any length, so you can get many combinations. But these are both generic ways to draw and represent an aldehyde, what an aldehyde may be like. The key thing is it's always connected to a hydrogen, right? There's no carbon chain on one of the sides for the carbon. There is on one, but not on the other. And if you put it on both sides, if you write it like this, well, then now you've got yourself a ketone, completely different thing. So let's focus on aldehydes for now. So all these sugar structures, at least the ones on my screen, we're talking about aldehydes. And there are 4 chiral centers, right? There's a chiral center here, 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 here. Chiral center means it has 4 distinguishing things attached. So, to this, there's something unique attached here, unique thing 1, unique thing 2, unique thing 3, and unique thing 4, right? And that's true for all these chiral centers that I'm coloring in right now for each and every diagram. Okay, we're good with chiral centers now. So you basically draw a line down the middle. You draw 4 intersections, right? So that's 4 carbons right here for you. You don't have to spell that out. And then there's a carbon at the end. And again, you don't have to spell that out. And looking at the structure that we just saw, this backbone right here can be the R of the aldehyde, can be the R of the aldehyde. This right here is the carbon, right? You see me scribbling. And then we just need to draw oxygen, right? You can draw it this way, double bond to oxygen and 1 hydrogen, or you can draw it the other way. You can choose to draw double bond to oxygen and the hydrogen. Doesn't matter. And at the very end, that's 1, 2, 3, 4, 5. There's got to be a sixth carbon. And fine, we'll, instead of drawing it as a dot, we'll spell it out. There's got to be a CH2. And sugars are carbohydrates. So there's a carbon, there's hydrogen, and there's also oxygen. So I'm going to put a OH. That's the hydrate part. Now, all of these things have an hydrate. So let's keep it simple. And this is where the question about, so now you know what 6-carbon monosaccharide with 4 chiral center looks like. It's a line with CHO on top, right? And 4 intersections and CH2OH on top, on the bottom. Now we know the skeletal structure. So now what it's about is, if somebody asks us to draw all the permutations, or just for our general knowledge, we're thinking about something, we're reading a chapter, and we really need to quickly come up with all the permutations in order to make sense of things. How can we do this without trial error or memorization? And so that part starts now that we've got the skeleton down. Really, you've got to put OH everywhere. So we'll keep it simple. We'll just put OH everywhere. And hydrogen on the other side, because that's the very definition of a carbohydrate: carbon, hydrogen, and the hydrate, which is the OH part. So now we got carbohydrate. This is the simplest one. And if you look at the diagram on this side, that's been given a name, allose, or however you pronounce that. We don't have to memorize that name. The important thing is we can tell at a glance that it's a sugar and it's a version of the sugar. And there are different versions based on how molecules are arranged, right? There's the next molecule is arranged this way. And it can get confusing about how to do all these arrangements, what to flip, what not to flip. And if you don't do them in a certain order, you will get confused. And that's when you start wondering, is there even an order to these things? And apparently there is, and that's what I want to share. So if you treat it almost like a binary language, then it becomes easy, right? So treat all the chiral centers as such. I'm going to write next to this structure, which is right here. So I'm going to say, okay, after I draw my diagram, I'm always going to number it. So if the hydrogen is on the left side, I'm going to number it 0, 0, 0, 0, 0, right? And if you know binary, that is literally 0. So I've already drawn that 0, 0, 0, 0. And that's my first one in the diagram is allose, right? That's first combination. Let's try a few more. So I'm going to draw a line CH2OH, right? 4 intersection, 1, 2, 3, 4. Done. We're ready. We're ready with the skeleton. And I'm going to just copy that so we can use that over and over again. Now we have one combination. How do we get the rest of the combinations? Well, this time, I'll just write 0, 0, 0, but on the top, I'll change one thing, okay? So I'll bring OH on this side, OH, but everything else is hydrogen. And similarly, on the other side, the pairings are the opposite, right? So the only thing I changed was the first one, right? And if you look at that, again, in binary, I don't know how comfortable you are, that's 1, right? So combination 0 gave us one structure, and combination of 1, changing one thing, gave us the next one, which actually, if you look, is the second thing on the queue, which is Ultros. And you know what, I'm just going to number them 0, 1, just so you don't get confused. This was 0, this was with 1, right? And if you compare, let me try to pinch this. If you compare OH triple H, OH triple H, H then triple OH, H then triple OH, right? We got to the right place. So it's starting to make sense. Let's see if it continues. I'm going to paste this so we can do this quickly. Let's make a bunch. If we can get it done. Okay, so now, again, we're gonna keep this 0, 0. We already changed one thing, so now we're gonna change one thing here. So if you know anything about binary, you know that 1, 0 represents 2. And if that's hard, maybe this analogy is not working for you and you should find another way to do things. But if binary works for you, if you understand that 0, 0, 1, 0, 0, 0, 0, 1 in binary is equal to 1 in base 10, and 0, 0, 1, 0, which means 2 to the power of 1, 2 to the power of 0, that basically means 2, right? This meant 2 to the power of 0, which was 1. And let's keep going. So let me just write that out first. So 3 looks like this, 2 to the power of 1, 2 to the power of 0, 2 to the power of 1 again, because those are both 1s. So that adds up to 3. And then 0, 1, 0, 0, 2 to the power of, let's see. Sorry, I messed up. 0. And let's keep going. 2 to the power of 0 is 1, right? Yes, okay. So yeah, 2 plus 1 is 3. 2 to the power of 1, 2 to the power of 2, 2 to the power of, no, I'm doing something wrong. Yeah, no, I'm doing it right. Okay, so let's keep going. That comes out to 4. And similarly, you will get 0, 1, 0, 1, which will 2 to the power of 2, 2 to the power of 0. So that will come out to 5, 0, 1, 1, 0, 2 to the power of 2, 2 to the power of 1. That's 4 plus 2 is 6, 0, 1, 1, 1, 2, 2, 1, 0, and that's 7. Okay, and maybe we'll stop here because we got 0, 1, 2, 3, 4, 5, 6, 7. That's 8 combinations. Hopefully that's seeable. Okay, let's keep going. So let's get ready. 0, 0, 1, 1, 0, 1, 0, 0, which means 3, which means 4. And okay, let's keep everything the same. H, H, OH, OH, H, and this is a 0. Don't want you to confuse it. Right there. H, OH. Oh, these are zeros. Okay, fine. H, OH, OH, H, and change it here. Okay, so here we flip it. OH and a H. Here we flip it. OH and an H. OH and an H. Okay, so let's see if we're keeping some kind of linear sequence that's not messy and that won't confuse us. Let's take a quick look. So we already looked at number one. Let's look at this one, right? What did we get? Oh, I didn't write it down. H, H, H. Standard procedures for these, and then flip just one, right? Okay, so what's number two? Let's take a look. It represents HOHH. Let's go take a look. HOHH, right? We got it right. And on the other side, OHHOO. You get it. Let's check the next one. HO HH. HO HH. Got it. Let's go beyond that. Okay. The fifth one. Triple H and then one OH just above. Triple H and one OH just above, right? That's what's going on. And again, memorizing names, other than memorizing names, which can be challenging, you kind of get the gist of it. If you go and if you treat it like binary and you go 0, 1, 2, 3, 4, 5, 6, 7, 8, by the time you get to the eighth combination, which is right here, right? 0, 1, 1, 1. Well, guess what? Here was the 0, so that's just H. And then 1, 1, 1 here upper means flip all these three, which we did, and now we're at the last one. So that's an easy way to quickly get at all the permutations. One thing somebody may be wondering is, hey, wait, if that's true, how come you're not flipping this last digit? Well, that's because that would be the L configuration. If we flipped the first digit and then tried 1 0 0 1 0 1 0 1 0 1 1 1 0 1 0 0, and there will be 8 more combinations once we flip this digit, the biggest digit, and that would actually represent the reflection or the enantiomers. They would represent the L configuration. And right now we're just looking at the D configuration. So in all honesty, because it's 2 to the power of 4, there are four possibilities, you can see that that's comes out to 16 combinations, right? 8 of those combinations, which we're shown here in this diagram, are actually in the D configuration. And the other 8 of those combinations would be in the L configuration. And just to give you an example of that, let me add a page so we can do some work. Okay, just to give you an example of that. This goes back to how we determine D and L. Let me just draw a skeletal structure that we are used to, CH2OH, right? That's just a skeleton, and then 4 intersections. The way you determine is you count down from the top, right? 1, 2, 3, 4, 5, 6. There are only 4 chiral carbons here. 4 chiral carbons right here. Everything else is not a chiral carbon because it doesn't have 4 unique bonds. So out of these 4 chiral carbons, you always look what's here. If there is a side group, like OH is considered a side group, right? If OH is to the right-hand side, right? Then right-hand side is dextro, and the D comes from there. So we would consider anything where the last ends up with OH, or the side group as they call it, as D configuration. So if you look at everything up here, OH, the last OH, which by the way, we denoted as 0, right? 0 means HOS, business as usual. The last OH in all of these was on the right-hand side, which means these were all dextro, right-hand side, dextro configuration. So now if I want to write the other 6 configurations, I'm going, I had been doing 0, something, something, something. So now if I make this 1 and I flip the other switches, right? One by one, I combine the other switches, then OH is on this side, and that is to the left. And left is, I think, just levo, which I think means left, so the L. So that's going to be the L configuration. So using binary, you can get all 16 combinations at once, but if you want to identify which one is dextro and which one is levo, you would say, well, all the ones that start with 0, those 8 combinations are dextro, D, right? The side group, the OH side group is to the right. And all other combinations, as you write down the numbers that start with 1, have the OH on the left side, so that's a levo, right? And together, 8 plus 8 is 16. And we should really have 2 to the 4, 16 combinations. Why? Because we have 4 places to fill with numbers. And there can be 2 numbers in each of these places, right? It can be 0, 1, 0, 1, 0, 1, 0, or 1. So that means we have, what is that? 4. That's 4. And that's 16 combinations. So hopefully the math behind it makes sense. Maybe it's scary, in which case you can figure out another way to do things. But if the numbers behind this make sense, then you have now a very quick way to identify levo and dextro from one another. And you also have a very quick way to draw anywhere from 8 to 16 combinations at a whim, as and when you need to do that.